Wallerstein in 1960, and then explained theoretically by Faulkner in 1966. You expect that the color of the horizontal branch is blue for metal poor cluster and becomes redder and redder so far you go to more metal rich clusters. However, the year after this very nice explanation, just a year after, it was found that does not work for many clusters, and there is a second parameter that is needed. This was work still by Sandage, Wilde, and Vandenberg. And this is the classical example of a second parameter effect. The M3, M13 couple, they have the same metallicity, but very different horizontal branch. Here it is very extended, but going to the red, and here is entirely in the blue part. There were 20, 30 years of trials to explain the second parameter effect. It was soon discovered that in principle everything works. That is, a lot of different parameters may really affect the morphology of the horizontal branch. Mass loss, which makes the horizontal branch bluer. Age, which also makes the horizontal branch bluer. Increasing age, the horizontal branch becomes bluer. This is essentially related to the fact that the sequence along the horizontal branch is a sequence in mass. So the higher the mass, the redder is the horizontal branch. Then helium content. Helium content is a more complex effect because it makes the horizontal branch brighter and bluer. The CNO abundances, which makes the horizontal branch render. And then it was found that there are correlation, for instance, with concentration of the cluster, which was thought to be link perhaps to core rotation. This was a proposition by Fusipeci and Bonanno in the 90s. All these make things very messy. It's not very easy to understand what it is going on. And the conclusion from all these studies was that more likely there is more than one second parameter. By the way, this is not simply a question of average color, but also of how stars distribute. For instance, these are two metal poor clusters. In this case, you have a very short horizontal branch in GC 4590. While in this other, which has more or less the same metallicity, there is a long blue tail. This is M15. There is a very long blue tail. So it's a question of distribution, not only of mean color. The first important progress to understand what's going on was the acknowledgement that the second parameter is correlated with galactocentric distance. This was done by Zinn in 1980, who found that the outer halo cluster tend to have a redder horizontal branch than the inner halo ones. And this was interpreted as an effect of age. Lee was a student of Robert Zinn and make these models, and he showed that this may be a sequence of age. That is, in the outer halo, the clusters are typically younger than they are in the inner halo. And for this region, they have this redder horizontal branch. The ages that were available at the epoch of 1990 were very poor, because the age of globular cluster requires very good photometry to be derived. Main sequence photometry at the epoch was not available, but then there was the launch of HST, and new very good data begins to be provided, especially when the ACS camera was available. And the various groups, in particular, there was a big public survey which was led by, I don't remember who, I think Piotto, I don't remember, but then in this they published a paper, first author daughter, which is a theoretician, on the interpretation of the age of the globular cluster. And they begin to derive quite accurate and reliable ages for globular cluster. And effectively, you see that this kind of correlation, young clusters tend to have a redder horizontal branch than bluer ones, is confirmed by this data. However, the situation is not so simple because there are clearly additional parameters required. It's not simply age. So it's not simply metallicity and age. It's also metallicity, age, plus some other things. And for instance, several globular clusters have very extended horizontal branches, much more extended than others. And this cannot be explained by metallicity age difference alone. Distribution of stars along the AGB, you should fix in your mind that the distribution of stars along the AGB is determined by their mass and by their chemical composition. And this leads to this link with the helium abundance. This is because helium stars evolve faster on the main sequence. Current helium-rich horizontal branch stars should be less massive. This was, I showed the diagram for NGC 2808 made by Franca, but actually the first who suggested this idea were Freeman and Norris in 1981. So it's still going back to 36 years ago. It is clear that there is a link with the oxygen-sodium anticorrelation. Redder star should be the progeny of the oxygen-rich sodium-poor star on the giant branch or the main sequence. And bluer star should be oxygen-poor and sodium-rich. This does not exclude that there are other effects, fourth, fifth parameter, but now we will fix on this third parameter. So this is the diagram I showed already given by Franca. Okay, so this is the correlation of the extreme of the horizontal branch, the hotter stars of the horizontal branch, the temperature of these hotter stars, with the sodium-oxygen anticorrelation. You see that there is a very nice correlation between these two quantities. Okay, so the idea was try to make something from all these things and try to understand better all these things. And so the idea was, okay, to analyze the photometric database using all what we know about the ages from main sequence fitting and all what we know about the variation in oxygen and sodium abundances. So I did this job some years ago. The first thing that I used is these ages from main sequence fitting. And these ages from main sequence fitting leads to an age metallicity relation for a globular cluster that is shown here. It seems a little bit messy, but actually it is not so terrible. It's quite clear that there are two groups of clusters. One group of clusters, which is the red ones, which are the disk bulge cluster, disk from the kinematics, disk and bulge clusters, and these are invariably the older ones that you have at a given metallicity. Okay? Then you have another sequence which is given by these inner aero cluster, which are blue circles, that starts more or less for similar ages when you are very metal poor, but go to younger ages when you are more metal rich. And they overlap to the clusters that we find associated to dwarf spheroidal. This is something that we should remind, and in the second part of the lecture I will come back on this point, which is very important. So essentially we have two populations, one which is likely linked to the main part of our galaxy, and the other part which is more linked to accretion episodes that occurred later. Okay, using these ages, and we also, the other part that we use is the measure of the colors. Essentially, I use three values of the colors for each cluster. One is the median color. The other one are the minimum and maximum color. Here I used not exactly the minimum and maximum, but 5% and 95 percentile of the distribution in colors of the cluster. And if I use this distribution, I found these kind of things. this kind of relation with metallicity. Okay, you see that there is an overall trend. Okay, this is the first parameter. And, but the trend shows some scatter, and this is relatively small scatter for the median color, but you can find much higher, larger scatter for the other colors. Okay, and if you fix to the red objects, they find, which are these odd globular cluster, they follow a quite narrow sequence, not linear, but narrow. And the blue ones, which are younger, tends to be above in this sequence. That is, they tend to have a redder color, which is in agreement with the idea that age is a second parameter. Actually, this median color is strictly related to the parameter HBR that has been used by Zinn in his analysis. So they are essentially measuring the same thing. 2808 is peculiar because it has a very bimodal distribution with nearly 50% in the blue and 50% in the red. And depending if you count more in the blue and more in the red, it stay here or stay here. These are the ground-based observation, and these are, the space telescope observation, these are the ground-based observation. So depending on what you are using, etc. as a sample, it jumps from one part to the other, because the median is where 50% of the distribution is. On the other hand, the parameter B minus V min, the minimum color on the horizontal branch, is closely related to the maximum temperature. Of course, because there is the relation between B minus V and effective temperature of the stars. The next step I did is to transform these colors into masses using models of horizontal branch. And now again, you see that for the median color, you have this relation, which is not linear, but relatively simple. For the masses of the star with metallicity. But for the minimum, there is quite a mess. There is a lot of the scatter here in the distribution. So the median color describes quite well something that depends on metallicity and on a second parameter. Here you need a third parameter to explain this part. Okay, if I use these masses and I relate them to the mass that the star had at the tip of the giant branch, according to the models, I may estimate how much mass is lost before, between the giant branch, along the giant branch, before the star comes to the horizontal branch. And if I plot this against metallicity, this very strange V profile that we saw before, this very strange profile here, and I also take into account now the ages of the cluster, all these things comes much simpler and seems come out a linear relation of the mass loss with metallicity. So these strange facts that you see are artifacts of the relation between mass loss, age, mass loss, and but they are relatively simple things at the base. There is a simple mass loss law can explain what you see for the median color of the giant of the horizontal branch. What I can do, what I observe is that, however, this is clearly not enough, because if I look at clusters that have the same age and same metallicity, they may have still very different horizontal branches. These are two in a couple that I selected to be exactly the same metallicity and exactly the same age, but they have drastically different horizontal branches. So it is not simply age and metallicity. And okay, using this mass loss law, I can go in the other way, start from the median mass of the star along the horizontal branch, consider the mass law and then try to derive an age for these objects, assuming that they have the same helium but different ion, the ion that we know for this cluster. And this is what I derive. Okay, this is first an internal comparison just to show that the internal errors are relatively small. The age that I derive, for instance, from HST photometry or from ground-based photometry, the two samples of photometry that I consider, they are well correlated each other. The case of NGC 2808 is due to this jump in the, because of the bimodality or distribution of stars in the horizontal branch. But the other cluster works very well. So the internal errors are rather small. But I then compare this age derived from the horizontal branch with the age that I can derive from the main sequence. And the result is that it's much more a scatter of points. The correlation is much poorer. Okay, there is a broad correlation, but it is not one-to-one. There is a big scatter in the points. And this scatter is much larger than the internal errors. No, these are only the clusters that I have. The difference between these is in the metallicity. This is shown here because these are now separated in metallicity. However, this is not the same meaning of the points before. Okay, this is a difference in metallicity. And, well, what we have is that the scatter is very large, especially at intermediate metallicity. These arrow bars, the arrows here, shows what is the effect of changing helium by 0.02. Because when I derive the ages for the moment, I assume the same helium for all the clusters. But if I leave it variable, I can adjust this difference. I can justify this difference. It's not a big difference in helium that is required. Only 0.02, for instance, here is, see the length of this arrow, almost explain the entire difference that we observe. Okay? When I try to reproduce the things, I have also to assume some spread, intrinsic spread of colors along the horizontal branch. Typically, this is not well reproduced. Well, sometimes it's well reproduced by Gaussian, but sometimes it's not. Okay, this is the things that we have to remind. Okay, so what I can do is try to derive the helium from this the correction that I have to make to the ages, so that I adjust the ages of the horizontal branch to be consistent with the age for the, from the main sequence. And if I do this, I may use helium or may use a difference in mass, is the same thing. What I found is that now there is a strong correlation with the absolute magnitude of the objects. The correction in helium should be very small for the very small cluster, should be large for the large clusters. There are a few cases that are a bit anomalous, in particular 47 TAC and M3 show a much smaller scatter in smaller offset in mass than expected. This seems to tell you that this is a somewhat peculiar star formation story, different from the other clusters. Okay, this is the same plot, but this time with helium rather than the mass. And you see that the helium required is not that large for most of the cluster. We are below 0.3 for most of the cluster. Only a small fraction of the cluster really requires these very high helium abundances. Okay, so what we can do now is to look at the correlation with chemistry. In this case, we use the maximum value of the bluest stars on the horizontal branch and see the bluest versus the reddest and see what happens. And what happens is that there is a correlation of this delta Y, against the values of the interquartile of the relation. Of course, this is not unexpected because we know that there is this correlation between the extension of the oxygen-sodium distribution and the color of the bluest star on the horizontal branch. So this is not unexpected, but this is shown here. And what you see is that, observe is that if you use sodium, it seems that there are a number of clusters in which there is some variation in sodium and oxygen, but very small variation in helium. While if you look at magnesium-aluminum anticorrelation, there is practically no offset in the correlation. You should start from zero here. While here you start from some spread in sodium and oxygen, even without any variation in helium, miserable variation in helium. Why it can be so in this way? In reality, the issue is that the production of helium and sodium is not done in the same evolutionary phase in a cluster. Helium is produced during the main sequence, and in intermediate mass stars that have a mass larger than 4 solar masses, some of this helium is produced on the main sequence, is dredged up at the surface by the second dredge up. The second dredge up is there are actually three dredge up mechanism episodes in the formation of stars. The first dredge up occurs when the star go out from the main sequence. For massive star, there is mass larger than 4 solar masses, there is a second dredge up. And then for practically all stars, there is also a third dredge up, which happens on the AGB. This happens at the base of the AGB, actually, the second dredge up. While the third dredge up occurs in a later phase during the AGB. But this is a peculiar characteristic of this object. The object has more than 4 solar masses. That does not happen for the less massive stars. The amount of the helium which is dredged up here is a strong function of the stellar mass. These things that the helium is produced in this way. The helium that you see, that you can then go to pollute the interstellar medium to form the second generation, comes from this kind of things. This is different from the hot bottom burning, which is responsible for the oxygen-sodium anticorrelation, which is a later phase in the evolution of the star, the AGB stars. So there is, in principle, no real reason because the two should be strongly correlated each other. There are two different phases of star formation that are involved. In reality, both of them go in some way with the mass. So at the end, there is a correlation between the two, but it is not a one-to-one. It's more complicated. In fact, since sodium and oxygen anticorrelation can be produced also by less massive stars which are in the range 3 to 4 solar masses may also contribute to the sodium-oxygen anticorrelation. You may have objects in which there is a variation in sodium and oxygen, but no variation in helium, or very small one. On the other hand, magnesium and iron requires magnesium requires higher temperature, so the magnesium-aluminum anticorrelation is only seen when you have the massive stars, more massive than 4 solar mass star, so the same that produce helium. So in this case, the correlation is closer. Okay, this is the explanation of the second dredge up, if you want. Okay, so we expect that there is a variation of the composition of stars along the giant branch, the horizontal branch, because we expect essentially that the stars that are on the reddest part of the horizontal branch are the progeny of the stars that are oxygen-rich and sodium-poor. So for this, they have less helium, and so they are more massive. And while the stars that are in the bluest part of the horizontal branch, they should be the progeny of stars which have higher helium, higher sodium, and lower oxygen. So we expect there should be a correlation along the horizontal branch in the composition. in principle, one can think, okay, go to the spectra and see if this is really the case. There is one big difficulty. The big difficulty is that there is a region here that separates stars that have essentially outer convective envelope from the stars in which there is only the outer part of the star is in radiative equilibrium. And this limit, which is called the Grundal gap, the Grundal jump also, means that here there is nothing that avoid the star to have diffusion and radiative levitation effects that completely alter the abundances or chemical abundances in the surface. The atmosphere is completely, the abundance in the atmosphere completely modified by these effects. So it's very difficult to use this part to determine what was the original abundances of the star. While for stars redder than this limit, this is possible. This is a big limitation because in many cases the objects that are very interesting are bluer than this range. However, some attempt was done to use this, and for instance, this was the original paper of 6752 by Sandro Villanova, but then there was another paper by Marino on M4. In this case, you really can have the horizontal branch is not so extended, and so you can really distinguish the two populations better. And this is the result that Fabiola obtained. You see that the stars that are on the red part, they are sodium poor and oxygen rich. The stars that are on the blue part are indeed oxygen poor and sodium rich, as expected from this general, from this idea. Fabiola has done also other papers, in this case is M22. We did a number of clusters, and in general, everything confirms this kind of trend. For instance, this is the case of NGC 1851 that I did in 2012. Again, I found that the sodium oxygen, as I said, the ratio sodium to oxygen, this ratio is low, that is high oxygen and low sodium, in the red star, and it is high in the bluer star. You see that there is a gradient also among the red horizontal branch. Even in the red horizontal branch, we have some stars that begins to be sodium rich and oxygen poor, but they are the bluest stars on the red part of the horizontal branch. There are other clusters in which we did these things, and we always find this kind of trends. So it's confirmed by the observation, with the limitation that we cannot observe the very extreme cases of extreme high helium. Okay, this is the first part of my talk. So on the whole, we think that essentially we have essentially understood most of the horizontal branch. There are at least 3 basic parameters: metallicity, age, and this effect due to the multiple population that should be taken into account. There may be also additional small parameters that influence a little bit the details of the distribution. For instance, the amount of mass loss, the variation from star to star that you have to put is not the same in all clusters. In some clusters you have to put a very small scatter in mass loss. In others you have to put some larger scatter. Why? It is not clear. So there is possibly that there are also additional parameters. But most of the results are now understood. And it's clear that it's a complex thing. When you have 3 parameters acting, it's much more difficult to disentangle the different effects, understand what it is going on when you have only one dominant parameter. Okay, so this is the reason of it required more than 40 years to understand the second parameter issue, is because there are many second parameters, not because people is not smart. Okay, the second part of my talk is on a somewhat different topic, that is the relation between the halo and the globular cluster. What is this relation? Well, in current cosmological model, the halo is assembled from essentially many smaller systems. The idea is that the metapoor part of the halo may be made of objects like small dwarf spheroidals. This works if the metallicity is below -2, but does not work for the metallicity between -2 and -1, because in this range of metallicity, the chemical composition, the dwarf spheroidal star, is different from the chemical composition of halo stars of similar Fe over H. The difference is, for instance, very clearly seen on the alpha to iron ratio, which is very different, and implies that the bulk of the halo formed much faster than the typical population, the dwarf spheroidal that we see now. So an idea is maybe that the first generation of globular cluster is telling you about what was the halo population, the halo formation. To show this, I will use, first I will show you, I try to show you a V movie, which is taken from the latte simulation, which is done by Wetzel and co-workers. This is a cosmological simulation of the Milky Way formation, which include a quite realistic feedback. The problem in the cosmological simulation trying to reproduce individual galaxies typically on the feedback. Feedback is how the things react to the formation of stars. And this is very difficult to be described realistically for the moment, because we do not know the whole physics that is involved. They try to do their best, and I will show now the movie if I can. Okay, this movie shows what should be the colors in the optical bands, the colors and appearance of optical band of a galaxy like our own when it is forming. See that this is the redshift value, and you see how the galaxy should have appeared more or less at this epoch, our own galaxy, according to this simulation. And so this is an attempt to reproduce these things. And you see that there is a lot of things happening during the early phases. This is Z equal the order 1. And still there are a lot of episodes of accretion, star formation, and so is certainly very different from a simple collapse of a spherical cloud into a disk that is the classical model for the formation of our galaxy. Then at the end of this simulation, something that looks like a spiral begins to appear in the center. You begin to see spiral arms and so on in a disk. Still there is accretion of other objects, and that cause some changes. And okay, so this is more or less a picture of what you should imagine should be the evolution. I'm not sure that this simulation is really realistic for our own Milky Way. It's what they have done is to take essentially I think the Millennium simulation, and from the Millennium simulation they extracted a small part which looked promising to be something that at the end should be our own galaxy, and they follow the evolution of this. Possibly it is not exactly how our galaxy is made, and also possibly the feedback mechanism is not yet tuned exactly as it should be. But in any case, it gives an idea of what you should imagine to be these early phases of formation of the halo. You should not think of a halo as a smooth thing where you for not clear reasons, sometimes form very big objects, is something which is much more dramatic. Evolution is much more dramatic with a lot of episodes of things that happens. And this, I think, is the basic from which we should start. That is, we should have this in mind. Okay, now my PowerPoint started from the beginning, so I have to go back to where I was. Okay, so this is something that you should keep in mind. The formation of the halo of our galaxy should have been something like that, okay? Then we start again from archaeology, because we don't see the halo while it was forming. We see it after 13 billion of years of evolution. And try from this archaeology to understand something. Okay, this is a plot where I put the plot of the distance from the galactic center against the mass of the galaxy within that distance that you should derive, assuming that each object that is plotted here is tidally limited. Okay? So if you have an object at a given distance, you can, and which has a given tidal radius, there is a relation between this tidal radius and the mass of the object and the mass of the galaxy. Okay, so since you may try to use, for instance, some estimate of the mass of the object, you may try to estimate the mass of the galaxy at this separation. Okay, so you may do this plot. This is this mass, and this is the galactic center distance. I put here for reference a Navarro, Frank, and Weil halo, I think, of 10 to the 12 solar masses, just to give an idea of where it come out to be. Okay? And I plotted here as a red symbol the bulge thick disk globular cluster from kinematics. They are classified in this way. It's blue, the inner halo globular cluster, again from kinematics. In black, the outer halo globular cluster. And in green, the dwarf spheroidals. Okay? And if you look at this diagram, what you see is that the globular cluster quite nicely follow on the expectation for a Navarro, Frank, and White halo. What does it mean? It means that they are tidally limited, really tidally limited. What you see is the tidal radius. In the case of dwarf spheroidal, they are clearly much up than in this diagram. What does it mean? It does mean that the light that you see, because the radius of the object is derived from the light, does not fill the tidal radius, because else you will derive extremely high mass that have no meaning. Okay? So the light does not fill the tidal lobe of the object, the Roche lobe of the object. There are a few objects below, and these are typically those that show very strong tails. And you see for 554, 66, Bal 5, Sagittarius, as I showed yesterday, they all have these very clean tails. So they are tidally disrupting now. Okay? So this relation is telling you that in principle you may think this of a whole family of objects, a single family of objects, but that behave different because they are at a different distance from the galactic center. So the dwarf spheroidal have a given evolution because they were far from our galaxy, while the globular clusters now are tidally limited. So their evolution, their situation is strongly linked to what happened in the galaxy, or their relation with the galaxy, actually, with the interaction with the galaxy. So the difference between the globular cluster and the dwarf spheroidal is essentially that the dwarf spheroidal formed most of their star before interacting with our galaxy, while the globular clusters, the two things are strictly linked at each other. You cannot simply distinguish the two phases.
Raffaele, there is even another slope suggested there. If you want to the boundary thickness, where we know that the Navarro, Frank, and White have
Here? Yes, but this is because we begin to have a lot of baryonic mass that contribute. It's not simply dark matter.
But also the but the Navarro-Freckle white is also used for the center of galaxy where there is the cusp core problem, and
Yeah.
we know that it doesn't work.
Okay,
That's why
but
it's another one.
this is related to this discrepancy here. But for the moment, I will not focus on this. Okay, another thing that you can do is coming back to this diagram that I showed the first day, the luminosity-metallicity relation. Okay, I showed that dwarf spheroidal obey a luminosity-metallicity relation, while globular cluster does not, and that the relation for the dwarf spheroidal is the lower envelope of the distribution for the globular cluster. Well, this is exactly what you expect if you leave an object evolving by itself, or rather you interrupt the evolution when it's forming stars because of the interaction with our own galaxy. And we can use also this second diagram, the fact that the given metallicity, the dwarf spheroidal luminosity is a lower envelope of the globular cluster metallicity, to try to have an idea of the fragments, the size of the fragments from which the globular cluster is formed. Okay? Because we can go back to this metallicity relation and see what is the mass needed for a dwarf spheroid to produce an object with the metallicity of the globular cluster. And clearly these are much larger than the metallicity of the cluster now because of the shape of the relation. So in this way, we can consider this line here is the same thing that we showed before, the relation between metallicity and the aftermath of the relation between metallicity and mass of the dwarf spheroid. And we can see that for each object, we can compare the mass that they have now, the cluster, expressed now in absolute magnitude, assuming a given mass to light ratio, with the luminosity of the progenitor, that we can derive from this assumption that the progenitor should be a dwarf spheroidal with a mass luminosity large enough to produce the metallicity of the cluster that we observe. And we have this kind of distribution. And we end up with the conclusion that the typical median progenitor of a globular cluster is some object that can have an absolute magnitude of minus 11, minus 11.5. That is actually typically more massive than Sagittarius. It's not so much different from Sagittarius, it's something similar to Sagittarius, or a little bit between Sagittarius and Fornax in this range of luminosities. So what we can think then is that the halo might have a strong contribution of stars that are actually formed in the globular cluster and are then lost. There is a difference between saying this and saying that they form in the same. There are two ideas about the mass of the globular cluster that we can think of. One is the mass of the globular cluster as we see now. And the other one is the mass of the star cluster complexes from which the globular clusters formed. Okay, these are very different concepts, and they can lead to very different conclusions. Okay, however, start with globular cluster, we know that the cluster lost stars by violent relaxation. There is on a longer time scale, there is evaporation. I want to emphasize the different time scales here. The first one is a few million years. The time scale for evaporation is billion of years, or hundreds of millions of years. However, if we fix to these two mechanisms, we think that there is a substantial fraction of the original globular cluster mass should have been lost. And this loss is more efficient among the smaller cluster, or clusters that happens to pass closer to the galactic center. Well, there are evidences that I showed in the first lecture about this mass loss. So the globular clusters are the survivors of a potentially much larger initial population. So we may ask if a major part of the galactic field halo formed in globular cluster, but then were lost. And remember that the major source is likely infant cluster mortality. Okay, how multiple cell generation may help? Well, in different ways, but the first one is this one. The second generation population is typical of globular cluster. In globular cluster, 70% of the stars belongs to the second generation. If you look at the halo, you find that a small fraction, only 2.5% of the stars are sodium-rich and CN-rich. Let us assume now that these stars formed in globular cluster, the second generation of globular cluster, and then evaporated from the globular cluster. And this is the reason of this object. Okay. You should remind that in general to reproduce the first generation with the typical composition of a jet core collapse is only 1/3 of the current total population. To reproduce the ratio first generation, second generation, in most models you require a very large fraction of the first generation to be lost. And this is quite a simple consequence of the fact that only a small part of the stars contribute to the Gratton nucleosynthesis. Okay, let us now compare the present mass of the globular cluster to the mass of the halo. The mass of the halo can be obtained from in situ star counts, and globular cluster from summing the mass of the globular cluster. To avoid contamination by the galactic thick disk, we used only, in the first things, we may use only the polar caps. We sum up the luminosity of all globular cluster in the ARIS catalog that are in that volume. You should assume some mass to luminosity ratio, which typical value is about 2 for globular cluster populations. So if you do this, you end up with that the mass in the globular cluster that are in this part, these are not the total mass of the globular cluster, these are the globular cluster that are in the polar caps. Okay? The mass of the globular cluster in the polar caps is about 4 million solar masses. Okay, you can do the same for the halo and consider the same volume and count stars and see what mass it come out. Come out a mass in the halo of about 3 × 10⁸ solar masses in the polar caps. This is not the total mass of the halo. This is the mass of the halo in the region that are far from the plane, projected far from the plane. So the mass of the globular cluster is about 1.2% of the mass of the halo. So a quite small fraction. We can repeat the same procedure, but not limiting ourselves to the polar caps, but using the whole value, halo value. There is more uncertainty in this value. But at the end, the results are very similar. The mass in globular cluster, in this case, come out to be 14 millions of solar masses. The mass in the field, 1.2 billion of solar masses. So the risk ratio is more or less the same. It's about 1.2%. Okay, but come back to the fact that 2/3 of the stars in globular cluster of second generation. Stars with a composition similar to the second generation in globular cluster make up 5% of the stellar halo. And if we assume that they are star lost by globular cluster, and that second generation stars are lost from globular cluster at the same rate as the first generation one. The star lost by globular cluster after the formation of the second generation came out to be 3.7%, because it's 2.5% divided by 2/3. Okay? So it came out 3.7%. So the consequence of this is that we have currently 1.2% of the stars in the halo, which are now in globular cluster, while 3.7% should have been in the globular cluster in the past, but now are in the halo. So you must sum up the two terms and conclude that there are 5% of the halo which was originally formed in globular cluster. And that globular cluster should have lost, on average, some 75% of their mass. So they were, in total, they were originally 4 times more massive than they are now. This does not mean that a particular globular cluster that we are looking at was 4 times more massive. Some of the globular clusters lose quite a small number of stars. Other globular clusters lose a lot of them. But on average, they lose this quantity. By the way, probably some globular clusters simply disappear. There isn't any more. Okay, but this is only after the formation of the second generation. But we know that the mass involved in the process of the formation of the globular cluster must be much larger than the mass of the globular cluster after the formation of the second generation. We know this because else we cannot reproduce their chemical composition. Okay? The bulk of the second generation stars formed from the ejecta of only a fraction of the first generation stars. Okay, let us now assume that this ratio is about 5 to 10, the mass of the first generation with respect to the final mass. It's a conservative estimate. It may be even larger. Then we came out that the mass of the star cluster complexes that at the center of which, or in some region of which there was the very massive object that came out to be a globular cluster, made probably something like 25–50% of the halo mass, and this is a conservative estimate, it can be larger than this. Okay? So, it can be larger because part of the mass lost by the polluters was likely not used to form the second generation. The efficiency of 100% is very unlikely. Much more likely is that there were mass lost, and part of this ended up in formation of the second generation. At the end, you conclude that the galactic halo might essentially be made by these first generation stars. Most of the mass of the galactic halo, possibly 50, but possibly more, may come from these episodes, big episodes of star formation that at the end produced the globular cluster, which is a small output of a much bigger event. There are several tests that we can do to show this. Essentially, we have to find if there are systematic differences between the first generation that we see in globular cluster and the field stars. If they are completely different, this does not work. If they are very similar, it may work. Okay? And there are many different things that we can do: the metallicity distribution, density distribution, chemistry, the luminosity function of the blue horizontal branch, binaries. All of them actually works quite well. That is, this hypothesis is not contradicted by any clear fact. There is no any obvious fact that says, okay, cannot be. It's not like the case of the dual spheroidal for building the inner halo, because in that case we see the chemical composition is clearly different. In this case, there is nothing that said that you are wrong. Still, there are some doubts. In particular, the main problem is this observation of the Fornax globular cluster. In the Fornax dwarf spheroidal, there are 5 globular clusters. This means that the Fornax has an exceptionally high specific frequency of globular cluster. I think is one of the objects, the galaxy with the highest specific frequency of globular clusters. It's even larger than typical elliptical galaxy. A typical elliptical galaxy has a specific ratio, that is a ratio between the globular cluster and the luminosity, which is similar to the halo of our own galaxy. Okay? But in the case of the dwarf spheroidals, this ratio is much higher. There are 5 globular clusters in spite that it is a very small galaxy. Yes, yes. But at least the specific frequency is defined against luminosity. And yes, it's like the key to understand what is going on. But the ratio, this very high ratio. And some of this cluster, at least 4 out of 5, show a sodium-oxygen anticorrelation, which is signature of multiple population. Okay? So there seems that you should expect that there is a lot of stars, which in Fornax that have the same composition of the globular cluster, but and that are in the field of the galaxy. The basis of this is the idea that the galaxy lived in isolation and did not lost any star. Okay? So there's a paper by Larsen that discussed all these things. He takes cluster metallicity from a given set of abundances and field star metallicity from another one. And they made a comparison, and they conclude that there are only 4 or 5 metal poor Fornax field stars for every globular cluster star, which means that this ratio between the two populations is 4 or 5, something of this order, and not the ratio then of 10, 15 that we expected. So there is too many stars in globular cluster with respect to the stars that we see in the dwarf spheroidals. If you look carefully, this is shown in this diagram essentially, where you see, okay, one cluster is no problem because it's metal rich, but the other 4 clusters are metal poor, and these 4 clusters gives a population of stars which is in excess of the luminosity function, the metallicity distribution of the galaxy. So these objects are too much, too many stars in globular cluster with respect to the number of field stars that you find with the same metallicity. And they say this kill, according to them, this kill this idea of a very big first generation, generating the second generation. Well, there are many details to be questioned in this analysis. Well, one cluster actually is consistently pure first generation. The ratio first generation to second generation is likely smaller in this cluster than in normal globular cluster. This is also the case for the Large Magellanic Cloud clusters. So the probability, the largest probability is that that you do not require this big excess of stars. Also, there are some issues about the metallicity scale because they use different way to derive metallicities for the clusters and the field stars, and the two are not really consistent. So all these effects can mitigate a bit this result. The total should be of the order of 10, 12 now, if you mitigate for all these effects. So not so far from the 15 that you could expect. But still is a little bit warring. And of course, another possibility is that this cluster, these stars, has lost a significant fraction of the meta-poor stars. And this may really, what may really happen is that the globular cluster tends to concentrate to the center of a dwarf galaxy because of dynamical friction. So they, after some time, they go to the center. And if then the galaxy has an evolution, an interaction with another one, or for instance with the Milky Way, the stars that are lost are preferentially those in the outskirt of the galaxy, where you find mainly field stars and not the globular clusters. So at the end, this also may bias your result. The population of field stars is depleted with respect to the population of the globular clusters. And this enhances the specific frequency. Another important result of this paper is, however, that if you look at the mass function of the clusters, typically it is found that they follow a Press-Schechter relation like this one. This is, for instance, followed by the clusters in M82, young clusters. But if you look at these clusters in the fornax, dwarf spheroidal, where the destruction mechanisms are much less efficient than in our galaxy, so you should be able to preserve much better the cluster than in our galaxy. You have this, that you have only massive cluster. There is no small cluster, there are only the massive ones. So why this happens? And this shows that there is still much to be understood about the evolution of globular clusters. So what I try to convince you is that globular clusters are complex objects hosting multiple generational stars, that they are the end result of the evolution of originally much more massive objects, and these objects are possibly the inner halo counterpart of dwarf spheroidal. Since they are much closer to the center of a galaxy, they interacted with the galaxy much earlier than the dwarf spheroidals, and so their evolution is completely different. They are now tidally limited. They have completely different situation, dynamical situation. But my idea is that the object formed from things that were not really different. They simply happen to be in a different position with respect to our galaxy. Currently, 1.2% of the halo stars in globular cluster, but likely 5% of the halo formed within globular cluster. The globular cluster, the massive cluster. But much more might have formed in the episodes that ultimate formed the globular clusters. This is the last biograph of my talk.
Questions? Already have one here.
When you said that globular clusters are the counterparts of dwarf spheroidals, that they just happen to be in the different place, do you mean that regarding dark matter as well?
In origin, yes. But the problem is what of dark matter happened, what was the relation between dark matter and stars after the interaction with our own galaxy, which likely is the triggering factor for the formation of this star, the episode which leads to the important parts of star formation that we see. Okay, so when that happened, of course, the two have a very different dynamical responses to this thing. The cross-section is completely different. One is a dissipative medium, the other one is not. So at the end, the two detached. And so if one wants to look for the galactic halo that produced the globular cluster, who knows where it is now? It is very difficult to know where it is the current position of this halo.
Okay, thanks.
Other questions? Here.
Yesterday you talked that the polluters in globular clusters should be probably AGB stars, but I have lost some slides from you. But did you mention that as process pollution should be also present in these intermediate and the third generation?
You didn't lost anything because I did not show, but okay, the S process are produced by essentially by the third reject mechanism. And the idea for these massive AGB stars is that they lose their envelope before the third reject phase, very early during the AGB phase. They had the time to do the hot bottom burning, but not time enough to produce the S process. Okay, I told you, and in a quite cryptic way, that the result of the nucleosynthesis that are used to explain the chemical composition of the second generation requires some fine-tuning of mass loss. And this is exactly one kind of the fine-tuning that you require. You require that mass loss occurs very early during the AGB phase. So the AGB phase is a very complex phase with different things happening one after the other, but so it's critical when you lose the mass, because if you lose the mass very early, you produce something. If you lose the mass late, you produce completely different nucleosynthesis.
In the first part, when you were investigating the second parameter or third parameter, you were classifying clusters in age and also metallicity, but those clusters had multiple populations. What did you take as age in that case? And especially metallicity, because usually they have these three horizontal ridge and branch.
For what concern age, the difference in age between the different population is extremely small. Typically less than 100 million years over 13 billions. So it doesn't make any difference practically. For the metallicity, the total metallicity is not changed. The pollution comes from transformation of one metal into another metal. Okay, so you transform oxygen into nitrogen. You transform neon into sodium. You transform magnesium into aluminum. But the total sum of the metals is the same. So it's not a change in metallicity.
No, but if you have a spread in metallicity, and that's the whole point of the multiple generation for the Milky Way, where the age spread is negligible, as you said, you can have the different stars with the different metallicity on the red giant branch landed onto different positions.
Yes, yes.
Yeah.
This is the first parameter. Metallicity is the first parameter. But for a given cluster, the metallicity is the same. Metallicity, total global Z, the sum of all the metals is the same. There is no change. The change is that it's distributed differently among the different nuclei.
I would like to explore this aspect that 1.2% of the population in the halo would have this oxygen-sodium inverse relation. No? Using this, explaining that only part of the stars in the halo would come from...
About 2.5% of the star in the halo has a composition similar to the second generation in globular cluster.
So then you can use this to say that, if important part of the stars in the halo are coming from globular clusters, it's the first population, no? And then he used this, the same number that I understood that it was derived in the halo of the Milky Way, to apply to the dwarf spheroids.
No, I didn't. This was when I spoke of Fornax. Yes. Okay. The idea there is that suppose that Fornax and the galaxy construct the clusters in the same way. Okay. Then if you suppose this, okay, then what you have is that you should expect that the clusters in Fornax have to produce the chemical abundance that you see in the cluster in Fornax should have been more massive than they are now. Say 5 times, 10 times. It's not the cluster that survive, it's the original things that formed this. And so you should expect that there should be, this object will end up. In the original idea, they went up in the field population of Fornax. Okay? So if they end up in the original population of Fornax, okay, we may count how many stars are there. We may compare to the how many stars are in globular clusters and have this ratio. Okay? This was an idea, quite simple idea. It came out almost immediately. I tried to make a first attempt using Sagittarius. It worked quite well for Sagittarius. And for Fornax, it was not clear for me at the moment how it worked. Then there was this paper by Larsen who showed these problems. Okay, so the basic idea is this one. You do not lose the star, the original star, because they are within the galaxy still. Okay, and so you have to produce this ratio. And clearly, the number of stars in globular cluster is very high there, so it's very critical. Okay.
But then this is, I think that you showed the application of these ideas in Fornax in M2 as well, yeah?
No, there is WLM.
Well, there are others, because for me
it's another galaxy.
Yeah, for me it's kind of too strong, the idea of using this number that was derived for the Milky Way to apply to dwarf spheroids. And then if you have only 2 or 3 cases, in one of those is like Fornax, that it does not, directly applies, perhaps it's because of this consideration.
The justification for this is that at least in some of the Fornax clusters, you see the sodium-oxygen anticorrelation. This is the justification for applying all this procedure also to the Fornax clusters.
Yeah, so my final question would be, how many dwarf galaxies people have analyzed deeply, as in the case of Fornax, for us to know if it's, if you really can apply this variation to the
Well, as I told you, I applied to Sagittarius, and the Sagittarius is okay. There are so many stars in Sagittarius that there is no problem to apply this procedure. And they applied to WLM, but the clusters, the objects were essentially selected because they have a very high specific frequency of globular cluster. That is because these are expected to be the most critical objects. If they have a very low specific frequency, no problem. So it's essentially related to this quantity. But on the other hand, it may tell you that these are the objects that have lost stars, rather than telling you that the mechanism for the globular cluster formation does not work.
Other questions? If not, let's thank our speaker for the 4 lectures that I liked a lot.
So now, in time for our last coffee break, we're just going to ask you to please do not bring anything from the coffee break, anything, mugs, cups, or anything in this side, because they're actually going to wrap up, clean up, and leave